Hi, my name is Paul Brebner. I'm the technology evangelist at Instacluster. And this talk is about building and scaling a robust zero-code streaming data pipeline with open source technologies. So I spend a lot of my time learning new open source technologies, building demonstration applications, blogging, and occasionally giving a talk. So thanks very much for the invite to present on this topic. This is the Instacluster managed platform. It's a complete ecosystem to support mission-critical open source big data applications. So we've got a whole bunch of open source technologies that we provide on different cloud providers all around the world. And this talk focuses on 3 recent additions to our managed platform, specifically Kafka Connect, Elasticsearch, and Kibana, and pipes. Puzzling pipes even. When I was giving a talk at Apache Con in Berlin a few years ago, I noticed all these blue pipes everywhere. I wondered whether perhaps they were for moving beer around the city. Pipes can be boring. This is just a very long straight one going from A to B. Some pipes can be fun or potentially dangerous too, I guess. But in general, pipes and integration in particular can be complicated. This is the pipe work for a rocket engine, for example. So I guess the question I want to address today is building a robust, scalable, zero-code data pipeline in open source a pipe dream? Let's find out. So one of the technologies we're using is Kafka Connect. It's a distributed solution to integrate Kafka with other heterogeneous data sources and stores. It comes with connectors, source or sink connectors, which handle the specifics of particular integrations, either into Kafka or out of Kafka. Why would you use Kafka Connect? Well, in theory, it provides zero-code integration. It's highly available, and it gives you elastic scaling independent of the Kafka cluster itself. The other technology we're looking at is managed Elasticsearch and Kibana. Elasticsearch is a scalable search system for indexed documents, and Kibana is for analysis and visualization of those documents. The one that we use is Open Distro for Elasticsearch, which is the Apache licensed technology. So what's the story? Well, last year I attended virtually, of course, the Kafka Summit, and they had a really interesting story about the American CDC. They built a Kafka specific, built a COVID-19 specific Kafka pipeline in under 30 days, which I thought was quite an impressive feat of engineering. And one of our Instacluster consultants built an integration demo using public climate data via REST connectors running on Docker, which I thought was also very interesting. So my idea was to use streaming REST public data sources and deploy the resulting application on the Instacluster managed platform for scalability mainly. So I went looking for public streaming REST APIs with easy to use JSON data format, complete data for an interesting domain, and that wasn't too political or apocalyptic, which sounded a bit impossible at the start of the search, but finally I found something that was suitable. So I ended up using tide data. So tides are quite interesting. They follow the lunar day, the Earth and the moon interacting in the way that this diagram shows, and you actually have a slightly longer than an Earth day for the period of tides. And the data was from the National Oceanic and Atmospheric Administration. They've got a website, so you can actually see what's going on, see what's available. Each of the blobs on their map shows some stations that measure tidal data, and you can drill down. So I thought, well, I wonder what the northernmost point of data in the United States is. And if you drill down there, you can have a look at the actual location. There's some photos. You can have a look at some sort of metadata about the location of the station. And if you drill down further, you can actually have a look at some of the tide data as well and see what sort of sensors are available at that location. And more important for my experiment, there's an API available and it's really well described. That's the URL there. And here's a REST example calling that API. So you have to specify a station ID, the data type, and the datum. So I used water level at the mean sea level, and then request how much data you want. So I just wanted the latest data point available and in JSON format. So there's an example of the call, and that returns the data that looks like that in JSON. So it's got two main parts, the metadata component and the data component. So let's start building a pipeline using this REST API for the data sources. There's one of the actual sensors. It's some sort of a microwave sensor, I think, which measures the water level. And that's essentially what's providing the data that we're retrieving. So what else do we need? Well, because I was using a managed service, I used the Instacluster console to provision the Kafka and Kafka Connect clusters. It's pretty easy to do. You just click on what you want. You select the cloud provider, the region, instance size, number of nodes, and security and other things that you want. And in this case, we also have to tell Kafka Connect to connect to a particular Kafka cluster and then provision them all. So very soon you end up with Kafka and Kafka Connect clusters. Here's a sort of an architectural diagram showing those two components and how they're going to interact with the outside world. So next we have to find a REST connector. And in our case, we actually have to deploy it to an AWS S3 bucket, tell the Connect cluster which bucket that is and configure the connector and then run it. This is to enable what we call bring your own or BYO connectors. And there's some instructions on our website about this. We actually have some default connectors available already in the Kafka Connect cluster, but for this experiment, I actually wanted to be able to try some other ones out as well. Now here's the REST source connector configuration, including things like the connector name, the class, URL, and topic, etc. So this ends up polling every 10 minutes. It writes the result to a Kafka topic. I picked a sample of 5 sensors to use, so there are 5 connector instances running. So now we have tidal data coming into the tides topic. What next? Well, next we have to provision the Elasticsearch and Kibana clusters, and it's a similar process using our console like this. And then you have to configure the default Elasticsearch connector, which is included in our offering to send the data to Elasticsearch. So here's an example of the configuration for that. You configure the sync connector name, the class, index, and topic. The index is created initially with default mappings if it doesn't already exist. Great, it's all working, well, sort of. Tide data is arriving in the tides index, but in the default index mappings, everything is a string. So to graph them as a time series by name, you actually need a custom mapping. Custom mapping basically means turning the T field into a date, the V field into a double, and the name field into a keyword. And there's an example of the call that you can use in Elasticsearch to do that. And the changes are highlighted in green there. Reindexing. Okay, so every time you change an Elasticsearch index mapping, you have to delete the data, or delete the index, sorry, and then index all the data again. But where does the data come from? Well, there's 2 options. In our case, using a Kafka sync connector, the data is actually already in the Kafka topic, so you can just replay it, or you can use the Elasticsearch reindex operation. So the hard part is over. Now we can start Kibana with just a single click in our console, and you end up on the Kibana front page. So there's a few more steps to be able to see the data. Here are the visualization steps. 3 main things you have to do. You have to have an index pattern to get the data from Elasticsearch. You have to create a visualization to create a particular graph type. And finally, you have to configure the graph settings to display the data correctly in the graph. And that's what we did. And here are the results. So this shows time on the x-axis versus the average tide level relative to average in meters for the 5 sample stations. So you can see a couple of interesting things. The first one is the one that we were hoping to see, the lunar day, the period of 24 hours and 50 minutes. So that's pretty evident. So it's really tidal data. The other thing which I perhaps wasn't expecting, which was a bit of a surprise, is that you can see the tidal range as well, which is the difference between the high and low tides. So some of them are actually quite big differences. There's one there near Bay, which is probably the biggest for this sample of data. That seems like quite a big tidal difference. So it turns out that tide range varies depending on a whole bunch of things, including the moon, the sun, local geography, and even weather. So here's a picture that's used to show some of the very high tide ranges that occur around the world. And interestingly enough, the high range sample that we saw is from near Bay, which is actually near that location where the arrow shows. Australia's biggest tide is here, which is in the Kimberley. It's actually got a pretty impressive thing called the horizontal waterfall, which is a result of the big tide difference there. So next I thought, let's see whether we could show this data on a map to show where the sensor locations are, perhaps to gain a better understanding of why the tidal ranges are so different. So this is the first attempt I had. This is the default base level map in Kibana. As you'll see, there's no data. So this turns out to be because there are no geo points in the data. So Elasticsearch doesn't recognize separate lat-long fields as geopoints. So a solution is to add an Elasticsearch ingest pipeline to pre-process documents before they are indexed. And then, of course, we have to re-index again. So yeah, you have to add the geopoint field to the index mapping, create the Elasticsearch ingest pipeline to construct the new field, and add as a default ingest pipeline to the index. And here we have the details. So here's where we add a new location field with the geopoint data type to the mapping and index. Here's where we create the new ingest pipeline to construct the new location geopoint string from the existing lat-long fields. And finally, we add location pipe as the default pipeline to the index. So now we have our pipeline transforming the raw data and adding the geopoint location data in Elasticsearch. And these are the mapping visualization steps to be able to see it. There's only 2 steps. We create a visualization reusing one of the existing index patterns, then configure the graph settings to display the data correctly. And if all goes well, you will end up seeing some data like this. So this shows the sensor locations, and the value that I picked is the minimum value over a period of a week. You can also add your own custom web map service layers. That's a bit tricky to do, but I succeeded, and you end up with a map that's potentially more detailed, and you can drill down and get more detail. There's a slightly strange thing about this map. It appears there's a big gap between 2 parts of the United States of America. I don't know what's supposed to be up there, but maybe another country. But what can go wrong? So for a while, everything worked fine. Then I noticed a few problems. The first problem is that the REST call can return a JSON error message. The REST source connector does not treat this as an error. So it's actually just sent through the system to the tides topic and eventually to the Elastic index as well. So the second problem is a bit more serious. The REST call can also return HTTP error messages. There's a bad gateway error message, for example, which can be returned. But again, this doesn't get treated as an error, so it's still sent through to the tides topic. Elasticsearch connector tries to read the HTTP error message and fails to the failed state, which means that the connector is no longer running and the data is not processed anymore. Luckily, with our system, the exceptions are viewable in the Kafka Connect logs topic. So I was able to diagnose this. So this was a bit surprising. I'd done some testing of the Kafka Connect framework before, and I had found that it does automatically restart workers if they are killed, like if you actually kill them on purpose. But surprisingly, it doesn't restart them if they fail into a failed state. So initially, I tried a simple workaround, which was just to monitor and regularly restart the failed connectors. This is a bit of a hack. That it did work, but it's not really ideal. A better solution, if connectors support the KIP 298 error handling in Connect, which not all do, unfortunately, then in theory, you can configure them to ignore input errors and also configure them so that errors are sent to a dead letter topic, so you can see if any messages have been missed. So where can we find connectors with more robust error handling? Well, I don't know whether the Australian outback is an obvious place to look, but sometimes you do see these signs that warn you of potentially dangerous animals on the road. Kangaroos, wombats, and yes, camels. So Apache Camel is actually a really interesting source of connectors. Interestingly enough, Australia has the most wild camels in the world, and Apache Camel has 346 open source Kafka connectors, which I think is the biggest set available anywhere as well. Apache Camel is a 10-year-old project for integration. It has lots of components, 355, which basically allows you to integrate with everything. So I was curious, where did so many Kafka connectors suddenly come from? So Camel meets Kafka. How do they do it? Camel Kafka Connector, it's a new sub-project which enables Camel components to be used as Kafka Connect connectors. How do they do it? Basically, automatically. They have automatic generation of connectors from Camel components. The source and/or sync connectors automatically are produced, which depends on which Camel components are available. Kafka connector configurations contain a mixture of Kafka Connect and Camel configuration information. So you need to read the documentation for both the Camel component and the Camel Kafka connector to understand what's required. And there's a fair amount of trial and error to find all the required fields. So let's take one for a test ride. Here's an example of a Camel Kafka Elasticsearch sync connector configuration. It looks a bit different to the other one. That's just because they are all different. And there's also some Camel specific information that you have to provide for it to work. So now we have robust handling of HTTP errors, and the connector keeps running. But unfortunately, the JSON error message is still passed through into Elasticsearch. Can we get Elasticsearch itself to reject the error JSON with something called Schema Validation? So here's an example of turning on strict schema validation. It's not real validation, it's really only preventing new fields from being defined in the Elasticsearch index. So now Elasticsearch rejects any JSON with an error field because it's not one that it knows about. But the connector still fails, and it turns out that it can't be configured to ignore sync side errors, unfortunately. This is going to be a future improvement. So my conclusions about the Camel Kafka Connect ecosystem. Well, the examples that I tried were certainly more robust than other open source connectors, so I decided to continue using them for the remainder of the experiment. So the final bit of the experiment really was scalability. How do we scale the pipeline? We're going to open the floodgates and see if we can increase the throughput. First problem is, how do we increase the load? Well, there's a couple of options. We could just replay the events from the Kafka topic. That's certainly a possibility, but you can't control the rate very easily. The second option is actually to replace the Kafka source connector with one that generates artificial data, and there's a few of these around, but I tried one called Kafka Connect Data Gen. So it's quite easy to control the load, and you can change, well, you can change the type of data, and in fact there was, not surprisingly, no tidal data, so I ended up having to change the story at this point into one to do a stock prices. Then for scalability, it's important to be able to measure parts of the system as well to make sure everything's working. But what to measure? There's an awful lot to measure. because mainly there are lots of systems and each system has lots of different metrics as well. So there's questions about which systems to be measuring. For the Kafka connector system, the source and sync components as well, the cluster, the connectors themselves, tasks, topics, etc. There's an awful lot of information potentially there that's relevant. So eventually, after a bit of investigation, I picked 7 metrics that I thought were particularly relevant, and I collected these with Prometheus from the Instant Cluster Monitoring API. So they're the ones that are in green there. And finally, these ended up being displayed on a single Grafana dashboard, which I thought was quite an important thing to be able to do, because you have multiple systems involved, you actually really need to be able to keep track of how each system is behaving as the data goes through the system end to end. So some parts of the system might be behaving quite well, but other parts might suddenly start misbehaving. So how do you scale the pipeline? Well, basically, it's to do with the tasks. To scale, you increase the load with the source connector tasks, so that increases the number of events going into the system. And then you have to increase the sync connector tasks to keep up, and you actually may need quite a lot more sync connector tasks than source connector tasks, because you've also got the target sync system is the final destination of the pipeline. And in this particular case, the Elasticsearch system is actually quite a lot slower than Kafka. Just to also remember that the sync connectors are actual Kafka consumers, and the number of Kafka consumers has to be less than or equal to the number of topic partitions. So you do need to configure things a bit to take into account the increased load as well. Were there some speed humps? Yes, there were a couple. There was one and number 2. And if you want to have a look at my blog series, the pipeline blog series online later on, you can see how we detected these problems and how we fixed them and eventually got the system to scale. So this is the final result. We managed to get linear scalability with increasing sync tasks. We didn't increase the system to a ridiculous throughput. We just wanted to demonstrate that it worked with the available resources that we had. So it does seem to work pretty well in terms of scalability eventually. So if you were going to build your own pipeline, what sort of things should you look out for? Well, here are some things to watch out for. First of all, you have to find a connector. You can either buy one, find an open source one, or even write your own. You have to configure it. Configurations are different. There's a lot of trial and error, lots of failures potentially, and eventually you've got to get it running, and it should run eventually. Transformation on the sync side may be required as well. And to test it out, you need to introduce source, sync, and other areas to check if it's robust enough. So I was a bit tricked by this. I thought the system was working fine for quite a few days, and then I started seeing all these errors and had to then introduce the error handling. You need to be able to monitor and scale it out, and watch out for things like unexpected failures, lag, particularly lag which increases, slow sync systems which involve more sync tasks, which require more Kafka partitions, which unfortunately also has the effect of reducing Kafka throughput. And finally, the capacity of the sync systems is actually critical as well. So yeah, why don't you try us out? We've got a trial of all of the technologies that I've been talking about today. So it's pretty easy to use, and that's exactly how I built this demonstration application myself. That's all from this talk. Thank you very much for listening. And there's some more information about this topic and some other ones to do with open source technologies on the blog and our website as well at instacluster.com. Thank you very much.